this mini course. I'm very happy to be here and to be able to talk at this nice place. As you see, I put a kind of agenda for my lectures on the board. I try to split this in three kind of parts and try to follow the program of the program, right? So it says about the probabilistic, quantum, and classical integrable systems, right? So it's a kind of nice triangle, right? I probably cover just two of the edges of the triangle, which is the classical and the quantum. Well, not only, sorry, I cover actually all three edges of the triangle, right? I mean, you'll see the second and the first, but in the second and the third lecture, I will cover dissipative quantum systems as well. So probabilistic quantum systems, today I will start with closed quantum systems or closed classical systems, and another kind of common kind of theme which I will try to use in my lectures will be I will be presenting all the material on the in the context of circuits. So circuits are, it's a modern word, right? Because it's very close to quantum simulation, but it's just another word to say that I will use discrete time dynamical system approach rather than continuous time. So I would prefer not to write much or almost any Hamiltonians, but I try to write everything in terms of gates or layers of circuits, which will be generating time evolution in discrete time. So actually, this is not a limitation at all. I mean, it's just a more general framework, right? I mean, you can always take the total limit if you like to see the Hamiltonian at the end. But I try to present all the stuff in the context of circuits, which is also much maybe closer to vertex models or to stochastic 6-vertex model, which will be kind of the mathematical model in the background of my, of most of my examples. Even though this will not be the standard stochastic 6-vertex model, but it will be the unitary 6-vertex model, which will be generating unitary dynamics, at least for today. Maybe tomorrow it will be slightly more, slightly different thing. But okay, so let me, I'm sorry for, I see a couple of experts here, and I'm sorry for those who will find maybe the first half of my lectures rather boring, but I have to set the stage. So today I will discuss integrable circuits, quantum and classical. I will start with the quantum circuits, quantum integrable circuits, which will simply follow from unitary solutions of Yang-Baxter equation. I show how this works. How can one get from arbitrary unitary solution of Yang-Baxter, how one gets unitary, how one gets a circuit which is integrable, which has infinitely many conserved quantities, which has some universal physical properties, which are still conjectured, but they're kind of very interesting. For example, anomalous spin transport, or some even links to KPZ physics. I hope I will get to there at the end of my talk by showing you some slides, but I will start with kind of very elementary and basic things. And the second part of today's lecture, I hope I have enough time at least to go quickly through it, will be to show how this works in classical physics. I mean, how one can build classical integrable circuits out of some solutions of set theoretical classical Yang-Baxter equations. And this is very much analogous. I mean, this is one way of doing quantum classical correspondence. People people speak of classical limits in very different ways, right? Some parameters going to 0 or to 1, things become kind of classical, right? But this will be another kind of way of thinking of classical limits. I mean, their circuits will become no longer unitary, but they will become some sort of many particle symplectic MEMS. Yeah? Which will be following, I mean, the local generators of these maps will be following from solutions of some set theoretic Yang-Baxter equations. Okay, this will be sort of the short summary of my today's lecture. And please interrupt me if there is anything kind of unclear or any question. I mean, I'm happy to discuss during the talk. So, okay, so what is the quantum circuit? The quantum circuit, I mean, what is the fundamental toolbox which we need to define to establish an integrable quantum circuit? So first, we start with a Hilbert space, right? Which would be a qubit. So this will be, let me start with lecture 1, right? And 1A, quantum circuits as quantum circuits as Floquet brickwork. So as local interacting. Quantum many-body systems. Quantum many-body systems. So, I mean, this is just the paradigm of quantum many-body dynamics, right? So, it's a Floquet dynamics. So, there will be discrete symmetry with respect to time translation, right? There will be no noise, at least not today. So it will be kind of Floquet, and the structure of the local interaction will be brickwork, right? So, I mean, most of you have seen brickwork structure, right? I mean, these are kind of the most dense and symmetric circuits, right, where you have translation invariance in space and time. So now we start with a fundamental toolbox, which is we take a local Hilbert space, which is a qubit, and then we take a gate, which is an element. It's a matrix over d by d. So it's a map over a tensor product of two local spaces, right? And graphically, I mean, of course, I will try to use as much as possible graphical notation. So graphically, I will denote this as U, which has two in and two out legs, right? And time for me will be always going vertically, usually from bottom up, but doesn't really matter, at least not when you have unitary dynamics. This will be time. And now there will be two states, ij, two values from 1 to d, if you want, going to two states k and l. And this will be denoting a matrix, which I will write as lower indices ij and upper indices kl. And the map U will be just a matrix. Again, here I will use kind of physicsy Dirac notation, right, which is common in quantum physics. So this is just a map which acting on ij produces a linear quantum superposition kl u ij kl. So right. So now this is a unitary map. I mean, if dynamics is quantum, this map should be unitary, right? So there is unitarity, and unitarity. I mean, now I will just try to be as compact as possible. So unitarity, I will write in diagrammatic way by placing two boxes U and U dagger on top of each other, right? If you take reverse time evolution, this is generated by U dagger or U star, the inverse unitary matrix. So if you have this diagram, then this is equivalent to just annihilating these two guys, right? I mean, this will be just ij. I prime j prime. Right, so this will be a delta product of two Kronecker deltas if you want. So, I mean, just to give you what this in diagram means. This diagram means, I mean, this is a tensor network notation, right? These beasts are tensors, right, which have three indices, I mean, three legs. And then when these legs are connected, then these indices are summed over. So these two indices are summed over. Let's call them K and L. Now, this is like multiplying two matrices, right? But since this is complex conjugate, since this is Hermitian conjugate, then I have to swap the indices and put a complex conjugate. So this is KL, IJ. Now, one is, well, this one is I prime, J prime, right? And this is a complex conjugate, right? And now this is just unitarity, right? Okay, so now what is a brickwork circuit? Well, brickwork circuit now is generated by an array of such gates, right? So now we define Hilbert space, which is a tensor product of L copies of local Hilbert space, where L is even for convenience. It doesn't have to be, but it's much nicer if you take L even and take periodic boundary conditions. Okay, so now we have this many-body Hilbert space H sub L. And we'll define two layers of the map. We'll define a map, which I call now a script U with subscript E, like an even layer. And this even layer will be just L over twofold tensor product of these local gates, right? That's an operation, a matrix which acts over the linear map, which acts over the entire Hilbert space. And then we take a shift. So this is the even layer. Then we take a shift map. Let's call it capital Pi, which is also a map over HL, and it maps as the product. I mean, the map is uniquely defined by its action on some basis, for example, a product basis, and it just rotates the product basis, right? By 2, by 3. Okay, so I'm talking about periodic boundary conditions, which means I will identify L plus 1, 1. And then once we have it, then we define the odd layer, which is pi even pi inverse. Okay, and then we define the Floquet operator. Floquet operator, it is one period of dynamics of a brickwork circuit, which is a product of U odd times U even. Okay, so now let's sketch it how this looks. We start with array. Let's do it for L equal to 8. I mean, if you look at quantum info literature, right, people usually write gates as rectangles and wires, quantum bits as straight lines, which go up or go even more commonly go horizontally. But I'm on purpose using this 45-degree notation, which is more reminiscent of a vertex model in diagonal orientation, right? It's actually very convenient because it really reminds us of vertex models and also of the symmetry between space and time. Now this is periodic boundary, so this one has to be hooked with this one, and there has to be this one coming there, and then all right, yeah, that's it. So this is 1, 2. This is L, and this is 1 prime, 2 prime. This is L prime. Okay, so now this is our use. And this part is U even, and this part is U odd. Okay. And okay, now simple example. Yes. Yeah.
Why is this called a Floquet?
Why is it called Floquet? Floquet is because it's periodic in time, right? It can be understood as a driven system where you switch on and off periodically with two-step protocol interactions on even and odd sides. Okay, so I mean, I give you immediately an example, which is trotterization of a Hamiltonian, right? Or local Hamiltonian, when you take a Hamiltonian with local interaction. You take a local interaction which only acts on two sides. Then you can take a local gate, which is e to the minus I tau h1, 2. And then now you can think of this as an approximation in the Trotter limit, but you can also think it as an exact identification of a circuit with a two-step kind of protocol of Hamiltonian dynamics, where you switch on and off interactions on even and odd bonds. Like you say, okay, you would like, I mean, this of course is an exact Hamiltonian, but you can say, okay, approximately for small tau, this is equal to U odd times U even, where U even is just product of and U odd is. Now I'll give you an example, which will be kind of our generic example, which I will use throughout most of my lectures, which is the XXX model or XXZ model.
Still, sorry. Can you get really some periodic? Can you get some Hamiltonian, which is really periodic?
Yeah. Yeah, I mean, you take a Hamiltonian. Okay, so let's call it a time-dependent Hamiltonian. Let's split it down now this into H even plus H odd, okay? Where even contains even bonds and odd contains odd bonds, right? And then you take Hamiltonian, which is even for time between 0 and tau over 2 mod tau, and odd for times between tau over 2 and tau mod tau. So you just take Hamiltonian, which has two values, right? Many body Hamiltonian, which has two values, H even and H odd. And then, I mean, people, when they do kind of various pulse protocols, right, in optics, they can realize Floquet Hamiltonians of different types using using this kind of pulse techniques, right? Now, this is just, I mean, I'm just justifying the name, why, I mean, identify this also with Floquet dynamics. Of course, for me, this is just, I'm not sure this is the best way to erase, produce lots of dust. But I mean, for me, it's much nicer is to just think of this as the more abstract way of thinking of many body dynamical systems. It's in discrete time, right? It's just that, you know, I like to think of discrete in terms of in discrete terms rather than continuous terms, because then things are like Lego, where you build stuff, right? You don't have to take any limits. But at the end of the day, it's very similar to continuous Hamiltonian systems.
When you take UE and U all to be kind of same, then in the continuous time limit, it becomes a simple homogeneous
Yes.
Hamiltonian, right?
Yeah. In continuous time limit, I mean, it's just a Trotter, this is just a Trotter formula then. Yeah. Okay, now. Let's make now a simple example. Yang-Baxter integrable circuit. Slightly wet, not sure. It's better. So this is an example. I started with an example, right? You can easily imagine how to generalize this by taking other solutions, but let's now take very, very well-known solution of the Yang-Baxter equation. Well, identity plus I tau times P, where P is a permutation, plus 1 plus I tau. So P ij, it's Pji, it's just a swap. And for example, I mean, this can be defined for any D, right? This defines an SUD invariant circuit, right? But let's now to really map to something well known, which is 6-vertex model, which we obtain for D equal to 2. And then U is just of this 6-vertex type, where A is 1 plus I tau, and B is I tau 1 plus I tau. Now think of stochastic 6-vertex model where tau would be imaginary. So this I tau would be a real number, which would be just a probability, right? Probability, this will be a symmetric 6-vertex model, right? Stochastic 6-vertex model. Now I'm just taking imaginary probability, and then this becomes unitary, right? Now you can easily convince yourself now that A square plus B square is 1. On top of that, that A plus B is also 1, even for imaginary probability, right? But now you can no longer interpret A and B as probabilities because they're complex, but A squared plus B squared is also 1. So it's kind of funny model. I mean, it's kind of all this sort of complex rotation really preserves this sum rule, but it in addition makes this probability quantum probabilities to be conserved, so to be unitary. Okay, so now this model, of course, is just a trotterized version of XXZ model. So for that, this Hamiltonian is just in the trotter limit. This becomes then just this model, but of course this model is integrable for any t, and then this becomes just an integrable SUN symmetric spin chain. And for all these models of this type, of course, and for many other models, U satisfies a form of Yang-Baxter equation, which is the Breit equation. I mean, this form, it satisfies the Breit equation. So U12 So U12, U23, U12 is the same as U23, U12, U23. And this, of course, is one way of writing Yang-Baxter equation, but maybe the more familiar one is to write U. We kind of need both. So I will rewrite this in terms of permutation. Now, these indices, of course, for those who are not experts, which probably are not many now, but the usual notation here in this business is that you use lowercase Roman indices to denote the spaces on which the map acts non-trivially. So these maps, of course, are matrices 4x4 in this case, but they are embedded into 2 to the L dimensional Hilbert space. And their embedding is such that these two indices tell us to which pair of spaces they act non-trivially. So, for example, for this equation to be spelled out, it's enough to consider the tensor product of 3 spaces, right? C8. And within C8, this equation is an identity. And you can rewrite it in a maybe different way when you take out the permutation, which in this case is trivial because permutation squares to 1. So this is kind of trivial here. But still, if you take out the permutation, you call the rest the so-called R matrix. And this R matrix satisfies the Yang-Baxter equation. So if you take these 3 particles or 3 spaces and you call them 1, 2, 3, then these 3 particles can have momenta. Let's call them lambda 1, lambda 2, and lambda 3. And this value of argument of the solution of Yang-Baxter equation, because this solution is defined with respect to a pair of spaces, this argument is just the difference of momenta corresponding to these 2 particles. So, for example, then we can say, okay, let's call lambda 2 minus lambda 1, let's call them tau, lambda 3 minus lambda 2, let's call mu, and so lambda 3 minus lambda 1 is tau plus mu. Okay. And now we just read this diagram. I mean, you never have to memorize Yang-Baxter equation. You just have to memorize the commutativity of this diagram, because then you just read time again in this direction. And when you read time in equations, you have to read equation right to left. So when you do that, you just start writing the scattering process, right? This is just a triple scattering of 3 particles with these 3 momenta. So start with this one. It's R1, so 1, 2 scatter, R1, 2. Of momentum lambda 2 minus lambda 1, which is tau. Then there is 1, 3 scattering of momentum, which is lambda 3 minus lambda 1, which is tau plus mu. And then there is then there is the last one is 3, 2 scattering, and 2, 3 is momentum mu. Momentum transfer, if you want mu. And now the second diagram is you start with R plus 3 on the right of mu, and then there is 1, 3 of mu plus tau. And then there is the last one is this one is 1, 2 of tau. Okay, so that's the Yang-Baxter equation, right? And now we will do simple manipulation. I mean, we need neither of this, but we'll need a sort of hybrid version, which we'll get by applying permutation P1, 2 on the Yang-Baxter. When we apply the permutation, this permutation can be pushed through, right? Permutation just flips spaces, right? When it's pushed here, it flips 2 to 1. Here it flips 1 to 2, and here it combines with R12 to give us a local propagator. So it's R13 of mu, R12 of tau plus mu, and then there is U12 of tau. And here, of course, you can immediately combine it with this guy. Okay. Right, now let's, of course, these are equations, but let's now write a diagrammatics, which is much nicer. Okay, before we start write a diagram for that, let me define a new variable. Let me define a lambda such that mu is lambda minus tau over 2, and mu plus tau is lambda plus tau over 2. Let's call this lambda minus and this lambda plus. So lambda now will be a spectral parameter entering the game, and this spectral parameter could be shifted by time, plus or minus tau over 2. Now this is the more symmetric notation, okay? So now let me define the symbols. And I will now just write tau here. This will be the local propagator. And then I will define an R matrix, which will be a diamond. I mean, usually in this business, this orientation is not so important because you can see things how from the connectivity of these things. But since for us time is always kind of having a well-defined direction, it's useful to either rotate or not rotate or rotate these things, right? I mean, for example, this is the time evolution, but no, this is not a time evolution. This is auxiliary space. So horizontal wires will be called auxiliary space. Vertical wires will be called physical space. Everything that can push in time direction is physical. Things which are all perpendicular, they are just auxiliary. Okay, so now here I will denote R matrices. I will call them R of lambda plus minus. Okay. And now what is this equation? Now let's write the diagram for this equation. This equation is just left-hand side, or we start with the right-hand side. Let's start with the right-hand side. Is this? We have two diamonds like this, and then we have this. Okay, so this is lambda plus, lambda minus, and this is tau. And this is equal to this guy, which is starting from below with the time evolution, and then do this, okay? Okay, so now this is 1, 2, 1 prime, 2 prime, and this is 3 space, and this is 3 prime, okay? We can always define an arrow, right? We can define an orientation in which these guys are running. Example is like this. And here it is tau, lambda. Now this is what happens when we flip, when we push the propagator through the pair of our matrices. What happens is that these spectral parameters get flipped, right? You see that this was lambda plus, lambda minus, and this is lambda minus, lambda plus. So up there is lambda minus, lambda plus. So just memorize this diagram because this is all that we need, right? That's everything that we need now. And the rest is just concluding. We're doing here. Use too much time for this, but maybe I can only show numerics tomorrow. Okay, now we see we can immediately make a statement claim the following transfer matrix. How we build a transfer matrix? We build a map over many-body Hilbert space. It should be a trace over the auxiliary space. Let's call this auxiliary. Then there will be an ordered product of J's going from 1 to L over 2, R to J minus 1, comma A, lambda plus, R to J, comma 1, lambda minus. And the following transfer matrix commutes with the time evolution. For any lambda. So that's basically proof of integrability. Now, since I'm running short on time, I will not write the diagram because it will take me 5 to 7 minutes. But I think it's completely obvious, right, what one needs to do. So I mean, I'm just writing the diagram for this transfer matrix, which will be a train of diamonds. And here there will be a trace, so these guys will be connected, okay? Now, so now what happens when I want to show that this commutes? I want to show that U tau of lambda is the same as tau of lambda U, which means I have to push U through. So I have to take one layer of U. One layer of U means I have bricks like so. Bricks like this. There are L over 2 bricks, right, in one layer. There is L diamonds, L over 2 bricks. I'm just sketching, right? I'm not doing it. I'm just sketching, but then I use this diagram, push this guy through. What I get is I flip lambda minus lambda plus. Then I do it again because I have to use 2 layers, and then I get exactly T of lambda back. So that's the proof. Now, there are two other things that you can show, which are both nice. Of course, this is completely general. It's for any unitary solution of Yang-Baxter equation. So the only thing we need is unitarity, but I will not explain now why we need unitarity. I leave it as an exercise because both of these other things I will just leave as an exercise. So that we can show 2 other things. So that Yang-Baxter equation and unitarity of U implies that T of lambda, T forms a commuting family. And the time evolution itself can be written in the form of transfer matrix, in terms of the transfer matrix. So you see, time evolution depends implicitly on one spectral variable, which is the time step. But this is not the spectral variable. That's a parameter of the model, right? But you can write the time evolution operator in terms of the of the transfer matrix evaluated at at 2 particular values of the spectral parameter, which is the parameter of the model, tau over 2 and minus tau over 2 and tau over 2. So now, again, for experts who know, of course, how to evaluate, how to get Hamiltonians from the transfer matrix, this is just a discrete time analog of the famous formula that a Hamiltonian is a logarithmic derivative of the transfer matrix, right? This should look to you as a kind of a discrete version of a log derivative or a logarithm. I mean, yeah, it's log derivative, right? It's the inverse and shift, right? So that's basically a log derivative. And okay, the proof I leave as an exercise, because it's just a repetition of this fundamental relation, plus you need this relation. We need this relation, and you can prove these identities. This is unitarity, right? Now, now you can have, from this also you can immediately derive local integrals of motion. So local integrals of motion have now two indices. One is a binary index, plus or minus. There are two sequences. And n is a sequential index, 1, 2, 3, 4. And this is the order of the derivative in the spectral variable of the logarithm of t of lambda evaluated at particular points plus minus tau over 2. So then you can show, because at that particular points, right, R matrix reduces to permutation, and when you have this string of R matrices in the transfer matrix, like half of them reduce to permutation. So this is enough to guarantee that this will be a local. I mean, something, because those terms which are not affected by the derivative, they will give us just the appropriate shift or permutation. And you can show that this will be then a local operator, an operator which is a sum of local terms. I mean, the proof is very similar to the proof in the Hamiltonian case, which is a standard proof in algebraic Bethe-Ansatz business. And right, but now what is kind of remarkable here is that there are two kind of strings of, I mean, two sets of conserved quantities, right? Qn plus and Qn minus, right? And you may wonder whether they're independent or not. I mean, well, I don't want to get to the discussion now, but you know, it's it's interesting. Okay, so now I think what I will do, well, maybe I will just make a short comment on what one can do when you have anisotropic. I mean, this of course was general, as I said. The explicit expressions were for XXX model, but we can immediately generalize this to XXZ model. XXZ model. That's a, I would call this a Floquet XXZ model. Floquet XXZ model. For Floquet XXZ model, you have U of lambda, which is 1 A B B A 1, and now A and B are just ratios of sines. Sine eta divided by sine eta plus lambda, and here it is sine lambda divided by sine eta plus lambda. And this, of course, can be understood. We'll erase this part. This can be understood as an exponential of XXZ Hamiltonian, sorry, sigma x cross sigma x plus j sigma y cross sigma y plus j prime sigma z cross sigma z, where this e to the 2I j plus or minus j prime. So there are these two exponents, j and j prime. These are the two kind of spin couplings. Jx is the same as jy, but it's different from jz. And then there is simple link between eta and lambda and j prime, which is these two equations, which have unique solution. Sine eta minus sine lambda divided by sine eta plus minus lambda, or minus plus plus minus lambda. Now, eta is the standard deformation parameter. So for those who prefer q, right, q is basically e to the I eta. So there are two solutions of this equation, right, which make physical sense. One would give us the easy axis, and the other would give us the easy plane XXZ model. So, for example, there are two solutions for which first one is lambda is imaginary and eta is real. And the second solution is lambda real and eta imaginary. Now, this one will be easy plane. This one will be easy axis. And lambda is connected to time, like this. Absolute value of lambda is the time step. I mean, can be interpreted as a time step. So the Trotter limit would be taking lambda small and yeah. Yeah. Okay, so I will discuss this a bit more tomorrow because I think I will, not tomorrow, on Wednesday, I will show some numerical experiments with transport in these spin chains. I'll try to argue, I mean, I'll try to discuss some conjectures in relation to KPZ physics, but I'll do this in the beginning of Wednesday's lecture rather. And today I will, because now we have this picture in mind, so I think I started 10 minutes late, right? So I have 20 minutes more, right? So that's right. So we don't need the computer today. I think it's better not to confuse the people. Yeah.
Thank you.
Yeah, thanks.
Yeah. So for the case of XXX, you mentioned some simple properties of A and B. A plus B is equal to 1.
Yeah.
And also modulus with
Yes.
inverse smear.
No, now A plus B is no longer 1 here, but unitarity is still there, right? So that's unitarity. That's still there. Okay, now let me, right. And okay, so now let's keep this in mind. I mean, I will continue with this for, let's say, 10 minutes with the computer slides on Wednesday before we go to boundary-driven open spin chains. But today I would like to continue with kind of analogous construction for classical circuits. Because I really like to compare this. I mean, this is like back-to-back calculation or derivation, right? So you may kind of find it a bit unusual, but if you compare it to quantum case, it's really kind of completely analogous. So, and in terms of physics, because this will be then also discussed with some numerics on Wednesday, in terms of physics, it's really identical. I mean, the physical features of the two models, the quantum and the classical, are essentially identical. So now, if you want, if you like more elaborate methods on integrable systems like TBA and GHD, then maybe classical spin chains are harder because their kind of excitation spectrum might be more complicated than quantum spin chains, but that also is something we can discuss. But at least the definition and the basic integrability structures are very much analogous. So now I'll discuss, classical spin. Classical SUN spin circuits. Okay, so now I will try to, so basically what I want to do is basically to write an integrable version of XXX or Floquet XXX model, classical XXX model, but I'm going to do it a bit more general. I mean, I will not limit myself to SU2 chains, but I will just go straight to SUN chains because the derivation is more abstract and even more kind of easy, right? Formally it's easier, and then at the end of calculation, we'll just put n equal to 2 and we'll find the discrete space-time Landau-Lifshitz lattice model. So what are we going to do? I mean, this is something that, to my flavor, to my taste, is the simplest classical integrable theory that I can think of. The space is discrete, time is discrete. It's a kind of automaton, but it's not a Celer automaton because the state space is continuous. We still think of classical spins or classical continuous variables, but the space-time is discrete. So we'll try to think of a simple kind of parallel transport problem or zero curvature condition on a discrete lattice, right? So let's take a discrete lattice, a simple zero curvature condition. On a discrete lattice. Of course, we will be interested in square lattice. So now we want to do something analogous to brickwork circuits. So our variables are living on a square lattice, but the auxiliary variables are living on a dual lattice. So let's take 4 points of a square lattice. Let's put them in circles. But then the points in the dual lattice will be somewhere here. So there will be a diamond like this. So now you can think of is going right in space-time, but now we have this the size of plaquette, right? And this plaquette will be, and now we have some classical variables. Let's call them M, M1, M2, going to M1 prime, M2 prime. So this will be some degrees of freedom, which will take values in some symmetric manifold. I will represent them as matrices with some constraints. But for the moment, it's not. For the moment, let's just think of them as matrices, right? I mean, for example, for spin SU2, for n equal to 2, for standard spin, these are 2 by 2 matrices, which satisfy some constraint, right? That's square to 1. So they can be written as dot product of a unit vector with the Pauli vector of Pauli matrices. But in general, these are just some matrices which square to 1. Okay, I will be more precise later. But now let me just define now an auxiliary problem, which will be a vector problem of dimension n. Okay, so here there will be to each of the links of this lattice. I will define. I mean, I will associate a vector in Cn, and then I will define a Lax matrix, which is a propagator from one point to the neighboring point. So there will be two types of Lax operators. I will call these ones L plus. And they will depend on some spectral parameter lambda, and of course on the physical variable that is carried along this link, right? So now let's think of a diamond lattice, and the dual lattice of links is a square lattice, and the dual lattice now carries physical degrees of freedom. So this will be M1 prime. This is L minus mu M2 prime. This is L plus. Now, in this direction, there is mu. In this direction, there is lambda. So mu, so all these guys have mu. All these guys have lambda. So all these kind of lines have some rapidity parameter, which is in this case lambda, in this case mu. And whenever they intersect, the difference between lambda minus mu is fixed. And this gives us a time step. This will give us a time step. So that's what makes sense, right? Okay, so now let's think of this parallel transport problem. We go from this point to this point. So we can either go this way or that way. And it should be identical, right? I mean, it should be kind of, the two transports should be identical. So I want to require that L plus M. So now let's look at this guy. So again, I mean, I start from right to left. So let's do like this. L minus mu M1 L plus lambda M2. Now this is this way. No.
The sign is wrong.
Sign is wrong, yes. Thank you. This is minus, this direction is minus, this direction is plus, yes. So it's okay. Now L minus L plus is equal to this direction, which is L plus L minus. L plus lambda mu M1 prime, L minus mu M2 prime. Okay, so now, I mean, this will be our equation of motion, right? This is a consistency condition for the equation of motion. Now the question is, what is really the minimal, kind of the most symmetric set of assumptions that we can put on constructing the Lax operator? This is what people call Lax operator, right? These are the two Lax operators, L plus, L minus. You can also call them as L and M pair or whatever. But since time and space are discrete, this is very symmetric. And now I try to advocate a set of three assumptions which will make life easy and simple, right? So we'll make the following simple assumptions. First assumption is that L is linear in lambda. Second assumption is that L is linear in M. So in spectral variable, in physical variable. And third assumption is L plus is the same as L minus. So which means that we will take L plus, which is the same as L minus, which is equal to lambda plus I times M. Okay, let's put I for convenience. So that's our assumption, right? What's simpler than that? There's nothing simpler than that, right? Can you think of something simpler? I don't. I mean, it's like in XXX model, right? Where you also have lambda plus I permutation. Now, I mean, this is even, oh, I don't know. Okay, now let's see what derives from here. So, I mean, you can now just write this out, and there is one more assumption that we make. There is a number 4 assumption, which is, which is maybe more strong, right? I have to confine myself to some compact manifold of matrices, right? And to do that, I will assume that M squares to 1, and that M is Hermitian. So this is my assumption about the manifold of matrices where I will live. And actually, it turns out that this assumption is not needed, but this assumption is needed to derive the consistency condition, right? So now, these assumptions then yield that M1 and M2 prime are given in terms of a map, which I will call as phi tau, as function of M1 and M2. So I will get M1 prime, M2 prime as a map, M1 by 2, and the map M1, M2, and the map is following. Just swap, and then you conjugate with some matrix, and that matrix is just a sum of the 2 matrices plus I tau. It's also very simple, right? So that's notation for, maybe for physicists is not completely obvious, right? It is M, A, and inverse. Okay, and now and tau, just lambda minus mu. So now we want tau fixed, so we want that all the lambdas and all the mu's are the same. And then we define dynamics in terms of, well, you have initial matrices, and then we have a map, which does this. And so on and so forth, right? So now we have, yeah. I mean, it's periodic boundary conditions, so yeah. Something like that. So we define our dynamical system, right? Which, let's call it now capital phi. I will now skip the details, right? You can understand easily how we imagine these things to work, right? You now compose these maps. Compose, I mean, you take a, I call this Cartesian product of maps, right? I mean, it's a tensor product. I don't know if you would call it a tensor product, right? You now define a phase space, M1, let's call it curly M is a phase space. And now ML will be M1 product L times, right? And now these maps, even and odd, will be now generated by a composition of local maps in an obvious way, right? Which will map ML to ML. Now I still have to define what the appropriate phase space. So what is the appropriate phase space? It turns out that this map not only looks nice, but also has nice features. Phi tau satisfies the following features. First, if M1 and M2, if M1 is Hermitian and M2 is Hermitian, then also the images are Hermitian. So it's hermiticity preserved. Then if M1 squares to 1 and M2 squares to 1, then M prime 1 squares to 1 and M2 prime squares to 1. And third, conserves the sum of the matrices. So this will be called SUN spin conservation, right? And this is like spin, it's like SUN spin. And yeah, the sum of the two matrices conserved. So this will be like SUN spin conservation. Now, what is now the convenient phase space that we can think of? Well, you see, I mean, these are matrices which are Hermitian. Well, you can consider them Hermitian, and they square to 1, right? So these matrices can be diagonalized, and they can be diagonalized like this, where sigma is a matrix which has 1s and minus 1s. Suppose it has k minus 1s, right? So we can write this as 1 minus m over 2 is a matrix which is a projector, right? And that's a Hermitian projector. And yeah, so this is basically, I mean, you can identify this space with the space of, if you fix k, with the space of Hermitian projectors with certain rank k. So of dimension n and the rank k. And this space is well known. It's known as complex Grassmannian space. Grassmannian. So we can think of this is a compact space, right? It's a space of projectors, right? If k is equal to 1, it's just a space of normalized vectors, right? Complex vectors, right? And so on and so forth. If k is 2, it's a space of mutually orthogonal pairs of complex vectors, normalized complex vectors, and so on. So it's a compact space, right? So you can think of M to belong to this compact space. And now the map is a symplectic map over this compact space. Okay. I think I should be closing right in a few minutes. So right. So now okay. So now what is the integrability? Why is this model kind of nice? Because it's integrable, and its transfer matrix and everything looks very much like for quantum spin. Well, I mean, the integrability structure looks very much like algebraic beta ansatz, even though this is a classical system. But the fact that it's kind of discrete time and that it looks like almost like a vertex model, I mean, allows us to write this structure in a way that looks very, very familiar. Now I have to skip a couple of things. I don't want to waste too much of your time. If anyone is interested, of course, you can check our papers. I mean, this is, maybe I should give a reference because it's not so well known. I mean, this construction has been derived in a paper by Ilievsky, Giga, is sitting there, and myself in SciPost 2020. And we call this discrete space-time matrix, integrable matrix models. But I'm not sure if it's a good name anyway. I'm not sure what would be a good name. Okay, but now let me just spend 2 or 3 minutes on integrability structure. First of all, there is a Poisson bracket, right? I mean, I will not go into details about constructing Poisson bracket. I just claim this is a symplectic manifold. This Grassmannian is a symplectic manifold and has a naturally defined Poisson bracket, right? Again, for n equal to 2 and k equal to 1, an example which immediately you know how you should treat is n equal to 2 and k equal to 1, right? Where these matrices are just S dot sigma, where S is a vector from R3, which is normalized, right? So S is a point on a sphere, and sigma is a vector of Pauli matrices, and this has all the properties. So this is basically the Grassmannian, right? Grassmannian can be identified with 2 sphere now for this case. And then, of course, you know how to do the standard spin Poisson bracket, right? But in general, there is also a neat Poisson bracket. But what I would like to do is just write transfer matrix, which and generator of constants of motion for this model. So now let's define a dynamical variable, which is the collection of matrices, right? And now let's define a monodromy matrix. or let's some spectral parameter lambda and collection of physical variables. And then this is the product of Lax operators, lambda minus and L, lambda plus L minus 1, and so on to lambda. Last one is lambda plus M1. Remember, L is even for convenience, and lambda plus minus is lambda plus minus tau over 2 as before. So that this is the staggered product of Lax operators, these simple Lax operators. So it's a matrix. It's a nonlinear function of physical degrees of freedom, right? This is Q's and P's, right? It can be written in terms of standard Q's and P's if you want, the momenta and coordinates and momenta. It's a nonlinear function of that, but it's a linear. It's a matrix in the auxiliary space, right? Auxiliary space is still a simple linear space, and of course we want to have now a function. So that's where define a transfer matrix. I call it. I mean, I don't like to call it a matrix because it's not a matrix. It's a phase space. It's a function of phase space coordinates. Is trace of this monodromy.
It's the monodromy matrix n by n.
Pardon me?
Monodromy matrix is n by n instead of 2 to the n by 2 to the n.
It's n by n, yes. It's n by n. I mean, the phase space is also always even dimensional. You can check that, right? The Grassmannian always has even number of. I mean, it's a manifold with even dimension, even real dimension. But yeah, I mean, this can be defined for any n being either even or odd. Okay, so now, right, so I'm almost done. I think I will just write this down and then I'll close and I'll just show you how to show that. I mean, just to hint you how to show that. So now, this zero curvature, this discrete zero curvature condition can immediately be applied to show the following. So discrete zero curvature condition implies the following, that this transfer matrix is conserved. Well, transfer, if you want transfer map, it's a map, right? It's not a matrix. It's conserved. So if you compose it with one time step of the time evolution, you get the same y back. And it's Poisson commuting, so it's an involution. And yeah, that's it. Okay. Right. So now let me just close with the formula for the. Now we have exactly the same formula for the conserved quantities as before. We have conserved two sequences of conserved quantities, Q plus minus, which are nonlinear functions of M, but they are local in the sense that they can be written as sums of local densities. Well, that's a good question, whether they are local. I mean, they are local if some condition is met, which I can discuss very briefly, and then I have to stop. Now, this is kind of curious. I mean, I find it kind of curious, and we still haven't dealt with that problem, but I think it's potentially an interesting problem. I mean, to discuss the locality of these conserved charges for this class of models, it turns out that if k is equal to 1, or k is equal to n minus 1, which is equivalent, right, for rank 1 projectors, then these guys are local. And you can show it using the standard Fatiev type argument. Namely, Lax operator at this particular pair of points reduces to a rank 1 projector. So that's enough to show that this has to be local. I mean, you need some analog of these shifts, simple shifts at the so-called shift point of the spectral parameter. You need a classical analog for that, and that is that the Lax operator should reduce to a rank 1 projector at these particular values of spectral parameter. Namely, I mean, you know, there is this lambda plus IM, and when k is equal to 1, this is rank 1 projector if this guy is 0, right? And at these points, tau plus minus lambda plus minus tau over 2, either lambda plus or lambda minus is 0. Okay, but the point is, what happens if K is not, if you have higher rank models which where dynamical degrees of freedom are higher rank matrices? Then I don't see this will be a local observables, right? I mean that this standard construction will not give us local charges. My conjecture, my kind of personal conjecture is that this will be quasi-local, but we have never done anything, and I don't see a simple way how to treat that problem. So, but I think it's an interesting problem. I mean, in particular, again, in the context of transport, right? I mean, because local charges are always useful for studying physics and transport. So it's not clear. I mean, this is, if you want an interesting open problem, I think I would like to see it answered one day. Okay, with this, I would like to close the first lecture and take attention.